So we will obviously start with the analysis part first, because that is a little easier to do. It gives us a better handle on what the finite state machine looks like, and it also allows us to define various components of a finite state machine. Okay, so let's start with the okay. I'm going to simply consider an example here so that we just deal with something very realistic. Okay, so I'm going to put this down. I have two flops, okay, and I'm going to control this through a common clock as usual. The clock till now we have always assumed is a common control signal, right? And I have, this is D, this is Q, D and Q. Okay, so let me call this as A and B, right? So this is an example from the textbook. So I will just keep the notation also pretty consistent with that, so that it is easy for us to follow and this thing. Okay, so now what I'm going to do, I'm going to add an AND gate here. Okay, and OR gate here, right? And I'm going to now feed this signal back to A. Okay, so I'm going to do the following. Okay, and the second input here is coming as an external input X, right? And I'm giving the same input here to the next, right? And next what I'll do, I'm going to take this B, I'm going to feed this back here, right? And okay, and I have the X that is routed here, and the same signal B is, okay, this is coming from A bar. Okay, so I'm going to assume that A bar is also available here and B bar is available here. Okay, so now okay, I believe I have reproduced this part correctly from the textbook. So I have D, Q and all that, right? So A bar, B bar, and my, it is X of t plus, yes, okay. So I think this is perfectly fine. And then I have my output circuit, right? So if you look at it, what I have drawn here is only combinational block 1, okay. I have to still draw combinational block 2, which basically is going to appear like this, right? And I have Y as my output. I have B and the other input is A, okay. So I have the input B appearing here and the other input is A. Yes. Okay, and what I have here is the complement of x going in as the input to this other AND gate. Okay, so the first thing to do is to recognize that any given circuit can be mapped back to this block diagram that I have drawn here. Okay, so if you were to just look at, what is it that is combinational block 1 and combinational block 2, it is as simple as this. If you look at this blue box here, it's the what I would call combinational block 1. Okay, and this one is my combinational block 2, right? So if I were to go back to this analogy here, number of flip-flops, my configuration here is n equal to 2, number of flip-flops, number of primary inputs m is equal to 1, and k is also equal to 1 in this example, because I have only one primary output, right? So my primary input is basically here, and this is equal to the primary output, and of course A and B, combination of A comma B are basically my states that we are talking about, right? And so now, given this circuit, what we want to figure out is what are the states that that this system goes through, right? And of course, the first thing we have to ask ourselves is how many states are there in this system, right? So of course we have because see what matters is not just the combination of A and B. So if you look at the system here, you have A comma B as representing two outputs of the flops, right? They can take only 4 different values, 0 0 0 1 1 0 1 1, but what we are interested in is actually the sequence, right? We are going to worry about if the flip-flop was in 0 0 state, then where can it go next? Okay, so based on this we are worried about all possible state transitions and not just the uh, number of possible outputs of the flops here. Okay, so therefore what we first do is we define what is known as the state equations. Okay, so what are my state equations? So the state equation is, I am just going to define the outputs, right? I am going to define next state, function of current state and primary inputs. Okay, and also I am going to define my primary outputs as a function of current state comma primary inputs here. Okay, it's a different function, it can't be the same function, so I'll call it G of this, right? So let us analyze combinational block 1, right? So what I have here is I have the output of the combinational block is actually going to these two things. So I'm going to call this as D. I'll not put D1 and D2 because I'm using 1 and 2 to denote the sequence of clock edges, right? So therefore I will call this as E and F. Okay, the output of these the input to the flops. Okay, so my E, right, which is basically the next state, right, of the flip flop, right? I'll also number them FF1 and FF2. Okay. So now if you look at combinational block 1, it takes A and B as inputs and X also as an input and provides an output for E and F. So if you look at this, E is equal to simply the input, I have this, let me, yeah, right. So let me just number them: N1, N2, O1, N3, O2, N4 and inverter I1. Okay. So output of N1, AND gate N1 is going to be A times X. So it will be A into X plus and output of N2 is going to be simply it is going to be B times X. B times X. Okay. Now clearly what we know is E is just the next state for the flip-flop whose output is actually A, right. So I will replace this with A n plus 1, okay, where n represents the time index, okay, the clock edge. Okay, remember when I say n plus 1, I mean this one here, okay, n equal to 1, n equal to 2 and so on. I am talking of that edge. So A n plus 1 is, sorry, A n times X plus B n times X. Okay. So the current state of A and B and the input X. Okay. Now on the other hand, the output F similarly, which is basically the output of N3, is simply coming from let me see, A bar, right, and X. Okay, so it is A bar into X. Okay, and we know that F is nothing but B n plus 1 equal to A bar A n bar into X, right. Now likewise the output Y is nothing but a function of let me see. So this is coming from B and A, right. So this is going to come as A plus B, okay, which is the output of O2, right, the OR gate 2, and then N4 is ANDing the inversion of X, so into X bar. Okay, so therefore implies Y is equal to AN plus BN into X bar, right. So therefore I can capture this entire state machine FSM using my state equations. My state equations, which happen to be A n plus 1 equal to A n plus B n into X, A n plus B n into X, B n plus 1 is equal to A n bar into X, Y is equal to A n plus B n into X, X bar. Okay. So now what we can do is we can also go ahead and define what is known as a state table. So you can capture this FSM using a state equation, or you can capture it using a state table. Okay. A state table so a state table typically all you have to worry about is is combinational block 1. Okay, how many inputs does it have? It has 3 inputs, right? AN, BN and X, and you just need to define the behavior for all possible combinations of this, right? And therefore I will say present state, okay, A and B. Then I am going to call the input, right, which is X. Then it will determine next state, okay, that is A n plus 1 B n plus 1. Actually I'll just call it A n and B n, okay, and my output Y, okay. So I'll partition this because what's on the right hand side is going to be my output of the, right. So this is A n and B n, okay. So you have 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1, right. So I have 8 combinations possible here, right, and I am going to simply determine if AN and BN were in this present state, what is my next state going to be, right. So all I have to do is take an OR of AN and BN, right. Look at this equation. In order to determine AN plus 1, take an OR of AN and BN, and therefore this will be 0, again into, so this will be 0, so this will be 0 0 1, and so it's an OR, and so this will be 1 0 1 0 1, right, 0 0 0 1 0 1 0 1, yes, okay. Likewise, what I have to look at for Bn plus 1 is simply look at An bar into X, okay. So An bar into X is, so all these are ones, so that means An bar, so all these are just 0. I don't even have to worry because An bar is straight away 0 in the bottom half, right. And then I am going to look at the top half only, so this will be 0 1 0 1, right, 0 1 0 1 and this thing, right. Now the output Y is going to be OR of AN and BN into X bar, right. So this will be 0 0, so this will be 1, this will be 0, right, into X bar, so 1 0 1 0, okay, 0 0 1 0 1, yeah, exactly, right. So with this, what we have been able to do is to capture the behavior of these state equations using a state table, okay. Remember, this forward path that we are studying here is so that we get comfortable to actually do the design of an FSM where we need to come backwards, okay. You could, for example, you may be given a state table and you may be asked to design an FSM, or you may be, given some other representation and asked to design an FSM. So you are supposed to work backwards from there and arrive at the state equations and eventually the circuit. So here we are just going in the forward direction because it's easy for us to get a grasp of all these, terms like state equation, state table and all that, and based on that we will, decide how to we'll infer some good design principles in the process, okay. So now, having defined what is a state table, we can also define what is known as a state diagram, okay. What is a state diagram. Okay, so here okay, so in this case, one second. Yeah. So in this case, what I can do now is to define 4 possible states that the flip-flop can actually go through. Okay. So I am going to simply look at the combination of AN and BN here. Okay. So I will define this state as 0 0, 0 1, right? 1 0, 1 1. Okay. These are my 4 states of the combination of AN and BN. Now if I had, instead of AN and BN, if I had AN, BN and CN, then I would have had 8 possible states, right? To power the number of D flip-flop outputs that I have, right? So now from here what I can do is I can go by, okay, if the input happens to be 0, what will be the next state of this, right? So all you have to do is you look at this input here, right? And then you say AN comma BN is present state is at 0 comma 0. The next state is also 0 and 0. Therefore, I will write an arrow like this, okay, which is, and then I will indicate the first 0 represents this 0 here. Okay, maybe I'll underline that. The first 0 represents here, and then I will say, in order to characterize this system fully, I need to also worry about this output, right? Therefore, I will write it like this, right? So, in fact, I will color code this here as X and and this guy in magenta as Y, so that the states are very clearly mentioned. So I will, in this also I will put it in blue, AN BN. AN plus 1 BN plus 1. Okay, yeah. Now I have the state 0 0 and the input can be a 1. Okay, so let me also number this as 1 to 8. Okay, so I have state 1, and so I'm looking at line 2 now. Present state is 0 0. If the input is 1, then I go to the next state, which is 0 1. Okay, so therefore I will make a transition now to the next state like this. Okay, again my input happens to be 1 and my output happens to be a 0 again, right? So 1 comma 0. Likewise, now I am at state 0 1, line 3 I am analyzing, right? I am at state 0 1, input is 0, and if the input happens to be 0, I go back to state 0 0, right? So therefore, okay, so what is this input line? This is line, 1, 2, 3. Okay, this is the third line. So therefore 0, 1, next is, so input is 0 and output is going to be a 1. Okay. Now I come to the fourth line and I am looking at the present state of 0, 1, and if the input is a 1, then I go to the next state of 1, 1. Okay. So this is my 1, 1 state for the fourth case, and the input is 1 and the output is going to be a 0. Okay. Now I am going to come to the fifth line of this table. So if I am at state 1, 0, that is this state. Okay, if I am at state 1, 0 and the input is a 0, then I go back to state 0, 0 if the output is a 1. Okay, so this is input 0 and output is a 1. Okay. On the other hand, line 6, if I am at state 1, 0 and the input is a 1, then I continue to be in the same state of 1, 0. So therefore, I continue to be in this particular state. The input is 1 and output is 0. Okay. Yes. And now I come to state 1, 1, line 7 and line 8. Okay, I am in state 1, 1 and the input is 0. I go back to 0, 0. So here I am. Okay, 1, 1, the input is 0 and the output is going to be a 1, right? And finally, if my number 8, line number 8, I have 1, 1 and my input is 1, then I go back to 1, 0. Okay, like this. So here again the input is 1 and output is a 0. Yes. So what we have now been able to do is to capture this entire state table using this state diagram. Okay, and like I said, how many states are there in the state diagram? We have as many states as the number of flip-flop outputs if they are D flip-flops. Okay, in fact, it doesn't matter whether it's D or JK, it's as many as there are number of flip-flops. Okay, 2 power number of flip-flops actually, yes. Okay, and but like I mentioned, what really matters is, unlike a combinational circuit where we were only worried about 2 power n inputs, we are now worried about number of possible transitions. If the previous input was something, what happens to the next input? So what happens is, you see that from 0, 0, you can, actually from 1, 1, you can go back to 0, 0, right? Or from 1, 0, you can go back to 0, 0, right? Or from 0, 0, you could come back to 0, 1, right? Or from 1, 0, you could choose to stay in 1, 0 state again, right? So all these transitions are not possible to capture using a truth table, and that's why you move to what is known as a state table here, which will allow you to go ahead and design this whole finite state machine in general, right? So with that, what I have done is to introduce you to various terminologies with which you can define a finite state machine in completion. So in the next lecture, we will look at how to use this finite state machine in order to um, you know derive these things, the state table and the state equations and so on appropriately.